In this section, we're going to be talking about more properties of the logarithms. The product rule says logarithm base b of the product of two expressions is equal to the sum of the logarithms with the same base b of one of the expression plus logarithm of the other expression. This is very understandable if we convert this property to exponential form. If we convert it to exponential form, we always start from the base b powered by this expression here, logarithm base b of m plus logarithm base b of n. Well, to power a number by sum of numbers is the same as to go a power by the first number times a power by the second number. Based on this property, this is the same as b powered by logarithm base b of m times b powered by logarithm base b of n. Now, property 4 from previous lecture says if that's the case, the two bases cancel and the result is m from the first part of the expression and n from the second part of the expression. So that's quickly the proof for this, for this property. But we want to think about this, that one logarithm can be split by two logarithms with the same base if m and n are in product. The quotient rule is proven very similarly. If that was a minus, the property for the minus a powered by n minus m is going to be a to the n times a to the negative m. Well, negative power brings the that base in the denominator, a to the m. So based on this property is that next rule called quotient rule. So if we have a quotient of two expressions, a logarithm base b of a quotient is going to be equal to the difference of two logarithms. The numerator is always positive and the denominator is always with a negative value. For a power rule, the power rule says if we have logarithm base b of m to the p, then that p can be moved as multiplication to this logarithm. And this property comes directly from from the product rule for logarithms. Imagine this is logarithm base b of, let's say, m squared, because it's easier. This means that's logarithm base b of m times m. Well, based on the first property, logarithm of a product reflects in a sum of two logarithms. And that's one variable plus the same variable is the same as twice that variable. It's twice logarithm base b of m. So that's just a demonstration, not really a proof, but I want you to get the idea how we are getting those three properties. So we are going to use those properties to extend logarithmic expressions. Logarithm base e, or natural log of e squared divided by 5. So I'm going to think, okay, that's a quotient rule. That means that's natural logarithm of the numerator minus natural logarithm of the denominator. Logarithm e powered by 2 based on properties of logarithms, or I can think from here e powered by what is equal to e to the 2. I can see that the question mark is equal to 2. So this first ln of e squared is equal to 2 minus ln of 5. Or I can also think about this question as use the power rule to move that 2 in front of the logarithm, and then natural logarithm of v is equal to 1, or logarithm base e of e is equal to 1 based on another property, or e power by what is equal to e, and that's a 1. So that is 1. So again, I have that 2 here. Of course, there are many ways to get to the answer, because those are all true statements. Those are all correct properties. They are supposed to not contradict each other, but in fact, they have to support each other. So multiple ways to get to the answer. For example, 2, that's a product of two functions, and the base is 10. So that's the same as logarithm of x cubed plus logarithm of base 4 based on the product property of logarithms, and then these exponents can be moved in multiplication 3 times logarithm of x plus, and I forgot my y here. Oh wait, completely wrote that, y to the 4 here, the 4 comes here, so that's plus 4 times logarithm of y. And I usually do that at once. I go, okay, how many things do I have to multiply here? 2 things, so logarithm of one of them plus logarithm of the other one of them, and then the powers I directly put up front. So that's another way when you get more comfortable with the rules. Another example, natural logarithm of square root of x divided by 100. Well, again, I have 2 expressions to consider, so I'm gonna end up having 2 logarithms. The numerator is gonna be the positive value, and the denominator is gonna be the negative value. And this square root of x, which is actually power of 1/2, can be moved in multiplication 1/2 logarithm of x. And logarithm base 10 of 100, 10 to the what is equal to 100, that's 2, so minus 2. And that's how we end up having this expression. That's my final answer. Now, example 4. How many things do I have in multiplication? Well, that's x to the 4, that's that root, and this is that square, so 3 things. So I'll end up having 3 logarithms. All of them have a base of a, so logarithm base of a, logarithm base of a. All expressions that are in the numerator, they will be positive logarithms. So x power by 4 here, that 4 I'm going to move in multiplication. X plus 5, the power of x plus 5 is, so you know what, I'm going to do it step by step. That's power by 4. So x plus 5, well, that's positive because it's in the numerator. And the power of x plus 5 is its third root, so that means the power is 1/3. And the last one logarithm is going to be taken from the denominator x minus 2, and x minus 2 is power by 2. And since it's in the denominator based on quotient rule, that's going to be subtraction. And then I'm going to put all the exponents in multiplication. And that's the problem is done. We expand it as much as possible. The opposite question is going to be condense the logarithmic expressions. So I have two expressions and I want to use the properties product, quotient, and power rule for logarithms to condense. Well, the sum of two logarithms is going to convert to a single logarithm when I multiply the arguments of those logarithms. And the simplest one is 6 times 9, which is 54. And that's how far we can go. For example 6, we're going to use the quotient rule because a minus sign. Again, logarithm with the same base, which is base 10 in this case. The positive arguments I'm going to put in the numerator and the negative arguments in the denominator. Example 7. Logarithm base 4 of x plus logarithm base 4 of x minus 3. It is a sum, so I'm going to go logarithm of product of the arguments. The base is still 4, so product of the arguments. And that's how far we can go. Of course, some of you may want to distribute here. Some of you may want to make that logarithm base 4 of x times x is x squared and x times negative 3 is negative 3x. But the best answer is usually in factored form, so I prefer this answer versus the next one. What is very important is probably we to put kind of parenthesis or bracket something to show that logarithm is to be taken from the entire thing. If I want to say 2 times logarithm base 4 of x, I usually do not want to say logarithm base 4 of x times 2, because then these two kind of is assumed to stay inside the logarithm, and that's not correct. The answer is different, and that's not what we mean. The last property is the example 8 is based on power rule for logarithms when we move the exponent logarithm base 5 of x to the 4, and that's how far we can go. Example 9, we are going to apply both product rule and power rule. We're going to move the exponents, the numbers here as exponents, and then since that's addition, we're going to have a product rule here with the same base, logarithm with the same base. X squared times x minus 4 power by 1/2 is the same as saying square root of x minus 4. So pretty much that's my final answer. And for example 10, logarithm, that's a common logarithm base 10, addition at the beginning, then subtraction, so I'll end up having a fraction, logarithm base 10, and I'll end up having a fraction. The positive logarithms would be in the numerator, the negative logarithm in the denominator. So x plus 8 squared moving this exponent here, then this 1/3 becoming exponent for x is going to be 3rd root of x. And then the negative logarithms, that 4 coming here as a power is going to give me x minus 4 power by 4. Well, this way we were able to condense and extend properties based on logarithms, logarithmic properties. So continue in the next